Welcome to my H5 video. As we can see, this is the circuit that I'll be using, and its power factor is 0.7 as calculated on Maple. So our goal is to correct the power factor to 1 by adding a capacitor in parallel to the inductive load. And so we'll be calculating the following values to compare both scenarios. Let's look at the process for the trisolve.
So before we corrected the power factor for the analytical method, all I did was calculate the impedance of the load, and then take that and calculate the voltage across the load using the voltage division, and then take those two values and use Ohm's law to calculate the current across the load network. And then for the complex power, I used the previously calculated voltage and current values, and then separated it into a real and imaginary portion so I can observe the real power and reactive power. And then we have the calculation for the capacitance that's needed to correct the power factor, and for this I just used the admittance and set it to 0 to solve for C, which is our capacitance. And then for the power factor, I took the cos of the difference between the phase angles of the voltage across the load and the current across the load. And then for after the capacitor is added, it's basically the same process except I added the capacitance that I found earlier into our impedance of the load calculation and added them in parallel. And everything else is exactly the same as I did earlier, which can also be seen in the report.
This is the circuit where the power factor has been corrected to 1 by the capacitor in parallel. Moving on to the multisim method. Here we have the scope connection for before the power correction, where channel 1 measures voltage from the source and channel 2 measures voltage across R3. I measured the peak to trough differences for each channel for calculating current to magnitude and the time difference for current phase.
So for the multisim portion of before the capacitor is added, what we did is take the peak to trough difference and calculate the amplitude of both channel 1 and channel 2 by dividing it by 2. And then using the amplitude of channel 2, which is the voltage across the R3 resistor, and dividing it by R3 to find the current across the load, which will be the same as the current across R3 because they're both connected in series. And then we have the current phase calculation using the time difference that we measured on multisim and converting it into radians using 2 pi frequency times the time difference. And then I formed the phasor domain of the current across the load just so I can use it for my voltage calculation that's below here. And so for voltage, I just did Ohm's law and then converted it into the polar form so I can observe the amplitude and the phase of the voltage across the load. And then for complex power, it's exactly the same as what I did in the analytical method section.
This is the connection for the circuit after the power factor has been corrected. Therefore, the capacitor has been added in parallel, and we can see the phase of both channels are the same, and the Maple process is exactly the same as before, except we just add in the capacitance for our load impedance. Moving on to the physical build. The probe connections here are exactly the same as multisim, and here we have just added 2 capacitors in parallel. As we have seen from previous methods, the graphs go from out of phase to in phase. Now we will look at the analytical results in depth. Comparing before and after the capacitor is added, we see that the voltage amplitude stays the same because the load impedance is much larger than the transmission resistor. The current amplitude decreases because once the load impedance increases after the capacitor is added and the voltage stays the same, mathematically meaning that the current should decrease. The phases go to 0 after the power correction as the capacitor shifts the current signal the opposite way, canceling the inductor's effect. So the power factor is corrected to 1. The power correction is evident by the complex power becoming completely real after the capacitor is added, since the source is relieved from having to provide an out-of-phase current to the inductive load due to the capacitor being able to do this, thus eliminating net reactive power. This increases the efficiency of the circuit and is an application of cost effectiveness when it comes to electricity bills. These results are seen throughout all 3 methods. This concludes H5. Thank you for watching.